Hello friends, our next topic is vestigial sideband modulation or VSB. As we know that SSB modulator works satisfactory for a speech or voice signals because in the spectrum of speech or voice signal there is an energy gap between two sidebands and this spectrum is centered around zero frequency. And due to this characteristic feature of the speech or voice signal, the transition band of the bandpass filter is adjusted properly so that one of the sideband is allowed to pass completely, whether it is upper single sideband or lower single sideband. But in the spectrum of wideband signals like TV video signals or computer data, there is significantly zero energy gap. So it is impractical to use SSB modulation in case of TV video signals or computer data. Here also the spectrum of wideband signals like TV video or computer data can easily use the double sideband suppressed carrier modulation technique. But the double sideband suppressed carrier requires the transmission bandwidth equal to twice the message bandwidth, and this breaks the requirement of the bandwidth conservation scheme. So to overcome these practical limitations, we need a method of modulation that compromise between the single sideband suppressed carrier and double sideband suppressed carrier modulation in its spectral characteristics. And we called the modified or compromised method as vestigial sideband that fulfill both the bandwidth conservation scheme and the practical applicability of the bandpass filter. Now we are going to discuss the VSB modulation. In VSB modulation, instead of removing one of the sideband completely, the trace or vestige of that sideband is transmitted. As shown in figure, our interest is to remove the lower sideband, so we take the trace or vestige of the lower sideband as a part of the transmitted signal. Therefore, this modulation is called vestigial sideband modulation. Here, the LSB is limited between Fc-W to Fc, and the bandwidth of the vestige is denoted by F suffix V, that is called vestige bandwidth. Typically, we take the vestige bandwidth as 25% of message bandwidth, that is capital W. Also, instead of transmitting the other sideband, that is upper sideband, in full, we transmit it almost the whole, so that the vestige part of the lower sideband compensate the upper sideband such that there is no information lost. And the transmission bandwidth of the vestigial sideband lies between the bandwidth of SSB, that is W, and bandwidth of the double sideband suppressed carrier, that is twice W. So it is equals to transmission bandwidth, that is FV plus W. Here FV is vestige bandwidth and capital W is a message bandwidth. Next we are going to discuss the generation of vestigial sideband or modulation of VSB. Here we use a special filter that is called sideband shaping filter, and for the generation of VSB we use a technique called frequency discrimination method or filter method. In this method, a product modulator is used that is followed by a bandpass filter. The bandpass filter is a specially designed filter called a sideband shaping filter, and its transfer function is denoted by capital H function of F. So we take a more attention on this sideband shaping filter. The inputs of the product modulator is message signal and carrier signal. And we get the output, that is the product of message signal MT and the carrier signal, that is AC cos 2 pi FCT, as a double sideband suppressed carrier signal. And this double sideband suppressed carrier signal is applied to a specially designed bandpass filter that is called a sideband shaping filter, having a transfer function capital H function of F. And by using the properties of the sideband shaping filter, the double sideband suppressed carrier wave get converted into vestigial sideband modulated wave, that is denoted by S function of T. Now we explain in detail using the graphical method. First, we assume that the vestige of the VSB belongs to the lower sideband of the double sideband suppressed carrier modulated wave, that is as shown in figure. Here we take only the positive frequency portion of the spectrum, and our purpose is to generate this vestigial sideband signal, having vestige or trace belong to the LSB of the double sideband suppressed carrier spectrum. For this, we use a specially designed bandpass filter that is called sideband shaping filter. The amplitude response of this sideband shaping filter, that is denoted by h function of f, is shown in figure. Here also we take only a positive frequency portion. Since this is a specially designed bandpass filter, its transmission bandwidth is Fv plus W, that is limited between Fc minus Fv and Fc plus capital W. Here Fc plus W is the upper frequency and Fc minus Fv is the lower frequency of the bandpass filter, and the difference between the two is called a transmission bandwidth, and it is equals to Fv plus W. Here typically the amplitude with respect to frequency f suffix c is 0.5 and the amplitude with respect to frequency Fc plus Fv is equals to 1. And in order to determine the vestige bandwidth, we take upper frequency as f suffix c and the lower frequency as Fc minus Fv. And with the help of this amplitude response of sideband shaping filter, we obtain the vestigial sideband. That is noted by capital S function of f. Here also we take only a positive frequency portion. The vestige of the LSB lies between frequency Fc plus Fv and Fc, that is carrier frequency, and almost upper sideband is passed through the bandpass filter, that is limited between Fc and Fc plus W. So the transmission bandwidth for the vestigial sideband is equals to Fv plus W. Here f suffix v is called a vestige side bandwidth that belongs to lower sideband, and capital W is the bandwidth of upper sideband, that is similar to the bandwidth of the message signal. And as far as the designing of the sideband shaping filter is concerned, the only requirement is that the transmitted vestige compensates the spectral portion missing from the other sideband. And to obtain this requirement, the transfer function hf must satisfy the following condition, that is h f plus fc plus capital H f minus fc should be equals to 1 for frequencies between minus W to W. Here f suffix c is called a carrier frequency. In the condition, the first term represents the positive frequency part of the bandpass transfer function hf, that is shifted to the left by fc, and the second term represents the negative frequency part of hf, that is shifted to the right by fc. So this is a condition that must be fulfilled by the sideband shaping filter to obtain the requirement for the generation of vestigial sideband. Next, we talk about the properties of the sideband shaping filter that follows the above condition. First property is the transfer function of the sideband shaping filter exhibit odd symmetry about the carrier frequency. So according to this property, we consider transfer function hf equals to u f minus fc minus capital H suffix v f minus fc. Here the first term is shifted unit step frequency function, and the second term is also a frequency function that is shifted by carrier frequency, and it represents a vestige as a part of the lower sideband. So the transfer function of the sideband shaping filter consists of two terms. First term is shifted unit step frequency function, and its value is 1 for frequency greater than carrier frequency and 0 for frequency less than carrier frequency. And the second term is also a frequency shifted function that represents a low pass transfer function, because here we consider a vestige as a part of lower sideband, and it is completely determined by the vestige of the VSB modulated wave. So according to the first property, the transfer function of the sideband shaping filter must exhibit odd symmetry, and this odd symmetry is given by the second term, that is totally depend upon the vestige of the VSB signal. This transfer function of the sideband shaping filter is band limited between Fc minus Fv and Fc plus W. Here Fc plus W is called a higher frequency component and Fc minus Fv is a lower frequency component. So from here we can determine the transmission bandwidth of the sideband shaping filter, and it is equals to higher frequency minus lower frequency, that is Fv plus W. Here W is the bandwidth of the message signal. Now we discuss more detail in graphically. First figure represents a unit step frequency function, that is U function of f, and its value is 1 for positive frequency, that is f greater than 0. And after shifting by a carrier frequency, we can represent the first term of the transfer function, that is U function of f minus fc. And for the second term, we consider an odd symmetric function that is used to determine the vestige part of the VSB signal, and it is denoted by capital H suffix V. So in order to represent the second term of the transfer function, we first translating the amplitude level, that is minus HV function of f. This also represents odd symmetry function with negative amplitude. And after frequency shifting toward right by the amount of carrier frequency, we represent minus HV function of f minus fc, that is shown in figure. So we can say that the second term HV function of f minus fc with negative amplitude exhibit the odd symmetry about the carrier frequency. Now after representing both the terms, we can obtain the transfer function of the sideband shaping filter. For this we simply add it. Now at frequency Fc minus Fv, the amplitude level is 0 for both the terms. So after adding, we get 0 amplitude level for the transfer function at Fc minus Fv. And at point Fc plus Fv, the amplitude level is 0 for odd symmetric, but there is a unit amplitude level for unit step shifted function. So after adding, we get a unit amplitude level at point Fc plus Fv. And accordingly, the negative peak of odd symmetry meet the positive peak and varies continuously. And from the designing point of view, the transfer function of the sideband shaping filter must be limited to Fc plus W. Here W is a bandwidth of the message signal. So in this way we get a specially designed sideband shaping filter for the generation of vestigial sideband. Now we discuss some point regarding to the sideband shaping filter. The first point is the transfer function HV function of f satisfies the property of odd symmetry about 0 frequency. So according to this property, HV function of minus f is equals to minus HV function of f. To show this property, we first consider the frequency function HV function of f as shown in figure. And after frequency translation, we get HV function of minus f by simply substituting f equals to minus f. That represents the left hand side of the property. Also, for the right hand side, we take the translation of amplitude level and we get minus HV function of f. Now, as we seen from the figure, the frequency translation and amplitude translation is same. So, in conclude that the transfer function HVF follow the property of odd symmetry about zero frequency. Second point is the transfer function HV function of f required to satisfy the odd symmetry property as shown above, only for the frequency interval between -W to W, where W is message bandwidth. So the transfer function of the sideband shaping filter, that is H function of f, have some arbitrary specifications for frequencies greater than Fc plus W. That is shown by a dash line. So with the help of this specially designed sideband shaping filter, we obtain the vestigial sideband from double sideband suppressed carrier wave. Here double sideband suppressed carrier wave is given by AC cos 2 pi fct into mt in time domain, and in frequency domain it is given as AC upon 2 within bracket m function of f minus fc plus m function of f plus fc. The output of the sideband shaping filter having transfer function h function of f is VSB wave, and in frequency domain it is given as s function of f equals to AC by 2 within bracket m function of f minus fc plus m function of f plus fc into h function of f. And by using the odd symmetry property of sideband shaping filter, we obtain the vestigial sideband.